Hi, my name is JAYRYAN JAVLES. My metric number is BS231109290. I'm gonna explain about the application of real analysis in our economy. Hi, so in economics, we know that there are two objectives that we usually hear in the class, which is for firms, it is to minimize our costs or to maximize the profit, and for consumers it's to maximize our utility or satisfaction or happiness. So what does relay analysis offer to be applied in our economy? We have a powerful tool in mathematical economy. It's called the Kuhn-Tucker condition. It solves optimization problem which extend the method of Lagrange multiplier, and it is crucial for analyzing resource allocation and decision making scenario. I'll explain more in the next slide. Right. Inequality constraints are very important for economists because they can use this to analyze resource allocation and production decision and market dynamics, which is very important for our economy. Understanding how inequality constraints apply to real-world economy situation enhances the practical relevance of mathematical economic models. This means that using this constraint, we can solve this mathematical model and achieve maximum or minimum goal. So another thing I need to remind is Kuhn-Tucker condition is just one of the many more applications of real analysis. So let's move on to the next slide. Hi, now we have our example that I'm going to show you. So our example of the Kuhn-Tucker condition is we're going to have a student, and this student will have to spend $100 in a month on two things: coffee and movie at the cinema. So it's a movie ticket. So our objective would be maximizing happiness on a tight budget. Okay. We probably see this in our daily life as well. Okay, so the information we know is the coffee is $5 per cup, and the movie at the cinema is $10 per movie. So one ticket is $10 and one cup of coffee is $5. So our goal is to maximize the total C, which is the coffee, and R, which is the movie ticket, without exceeding $100. So from this we can produce a constraint, like I said just now, our inequality constraint, which is 5C plus 10R less or equal to 100. This is our inequality constraint. And then we can have our objective constraint actually, but I put it as maximum utility, which is the square root C plus square root R. Okay. Then you can see the arrow. I hope you can try to understand. We are moving on to the Lagrange multiplier. Lagrange multiplier is the one you see with the lambda symbols. So you just plug in the formula, and then you will get the 5 lambda and 10 lambda. Then you just plug it in back following the arrow. Then you will divide the 5 lambda over 10 lambda. Okay, so you're gonna equal it, and in the end you're gonna get square root R equals to 2 square root C, and from this we can get C equals to 4 and R equals to 4. This means that optimal bundle would be the 4 coffee, and we have 4 ticket, totaling up to 100. So we have maximized our happiness on $100 budget. That is how you wanna apply real analysis on our economy. And of course, there's a lot more situation out there that can be used to give an example. That's all from me. Thank you for listening. Hope you can understand.
Hi, my name is Muhammad Alif Nazrin bin Muhammad ZURIN. So today I'm going to present and explain about the application of real analysis in engineering. In electrical engineering, real analysis is essential for Fourier analysis, which breaks down complex signals into simpler frequencies. This helps us design filters and clean up signals for better audio or image quality. Next, the control systems. Real analysis plays a major role in control theory, especially in using the Laplace transform to simply differential equations. This helps us design systems like PID controllers to maintain stability and accuracy. Next, mechanical and structural engineering. In mechanical and structural engineering, real analysis supports the finite element method, or we call it as FEM. Engineers use this method to simulate stress and predict how structures like bridge respond to different forces. Next, thermodynamics and heat transfers. Engineers use real analysis to solve partial differential equations that describe the distribution. This is crucial in designing cooling systems that prevent electronic components from overheating. Next, numerical methods and simulations. Real analysis is the backbone of numerical methods, which help us simulate and optimize systems when exact solutions are very complex. It ensures that our models are stable and give accurate results. The last one is probability and stochastic modeling. Real analysis also supports probability and stochastic processes. This is useful in quality control and risk management, where engineers predict product failures and make data-driven decisions. That's all from me. Thank you.
My name is Nabil and I'll continue with the application of real analysis in computer science. So first of all, we can see that there is an impact of Fourier and functional analysis with the help of real analysis. Fourier analysis has helped to redefine the hardness of approximation in computation problems and also enable the development of learning algorithms, circuit lower bounds, and probabilistically checkable proofs, which is PCPs. Second of all is Banach space theory and hypercontractivity. It introduced it to computer science by researchers like Kahn, Kalai, and Lineal, and it was originally used for Gaussian process, now applied to optimization problems, graph embeddings, and coding theory. The other one is role in unique games and approximation algorithms. Real analysis has helped computer science in techniques to help construct and analyze semi-definite programming, and it is used for Gaussian geometry and isoperimetry, provided deeper insights. Next, we have real analysis meets computational theory. John Neiman used Gaussian theory to improve results on surface area measurements. And another one is Anindia D applied Malevin calculus, a tool from stochastic analysis to de-randomization, making breakthroughs in learning and testings. Analysis also helped in advances in discrete analysis and combinatorics. The process in understanding Boolean cube slices using analytical techniques and led to a new results in external combinatorics, even in non-commutative settings.
Then the next part is about the application of real analysis in physics. Physics relies on precision definition and accurate model. Real analysis gives us the language and structure to build those models. For example, when we describe how objects move, how fluid flow, or how force interact, we using principle rooted in real analysis. It ensures our calculations are not just approximation but grounded in solid mathematical logic. Even more, advanced areas of physics like general relativity and quantum theory rely heavily on real analysis, whether it is analyzing signal, modeling wave, or understanding the curvature of space and time. Real analysis provides the foundation that make these theories reliable. In short, without real analysis, physics would lose its precision and depth. It's not just helpful but essential for progress in physics. As we explore more complex ideas and new theories, real analysis will continue to guide us, link abstract model to the real world.